Hi, my name is Molly Vick, and this is my Physics 2212 Lab 4 about circuits and capacitors. So here is an overview of my lab, and first I'll give an introduction including fundamental principles and ideas that I used. Then I'll go into my lab setup and lab procedure. Next, I will go into my experimental data, including observations and calculations. Third, I'll go over my results and compare my results. And finally, I will discuss the what if and why questions relating to the lab. So the key ideas and principles that I used in the lab, to start we have Ohm's law where voltage equals current times resistance. Next we have the node rule where the sum of current entering a node equals the sum of current leaving. This is the conservation of current. And finally we have the loop rule where the sum of all the electric potential differences around the loop is zero. So in this lab we'll be able to predict the behaviors of circuits with resistors in series and parallel. We will measure the actual values of conventional current and potential differences in currents, as well as assess the behaviors of ohmic resistors and capacitors. The system in this lab is the circuit, while the surroundings is everything else. The purpose of this lab is to use energy conservation and current conservation principles. And with that, our expected results, because the conservation of current and energy will be equal to the initial current or energy. So for conservation in series circuit, we predict that the current will be equal for both current 1 and current 2, and that it will be 0.02 amps. The total resistance will equal 147 ohms, and thus, using the Ohm's law, the current equals 3 volts divided by 147 ohms, which is also 0.02 amps. So in order to simulate the current as seen to the right, we measured I for the ammeter for both 1 and 2 currents to be 0.02 amps, and when reversing the connection, the readout of the ammeter stays the same. So the procedure continued. We have to first replace the ammeter with the voltmeter by making V equal to 3V and I equal to 0 amps. So second, we have to find a path of potential difference by using the loop rule. The sum of the voltage surrounding equals 0 as seen in this calculation below. And the pictures beside are helpful in understanding the procedure. So here is the graph of voltage, and so the graph starts at 3 volts because of the battery. There's a slight voltage drop after the first resistor, and then the voltage stays constant at 0 volts for the rest of the current. So here's some observations. So looking at the first question, the ammeter reading would change when you attach them. For the second question, connecting the voltmeter across the 100 ohms resistor, the reading gave current equal to 0.02 amps. Replacing the voltmeter with an ammeter in parallel with the 100 ohms in question 3, the resistor causes both current 1 and current 2 to equal 0.06 amps. This is due to the fact that the ammeters have 0 ohms. Therefore, there is no current that travels through the 100 ohms resistor. So looking at some more observations from our potential difference measurements in part 5 and 6, here are my calculations to find the resistance of each of the current elements for R47, 100, wire, and ammeter. As you can see, the first equals 48 ohms, the second equals 102 ohms, and the last two both equal 0 ohms. For resistance and capacitance circuits, I've set up with 9 volts battery, 200 capacitors, and a 30 ohms light bulb. I measured the voltage and discharge of the capacitor and plotted it for 20 seconds of voltage with time, and below are the formulas and data that was collected with this voltage over time. Here are some more calculations that I solved for. I found the resistance and capacitance to equal 5.88 when it actually equals 6, so the percent of source of error that I calculated was 2% error. The possible sources of error could be due to resistance within batteries or capacitors or even human error. In conclusion, I found that our experiments in the initial and final energy currents were approximately the same. So finally, I'll discuss the discussion questions for both the what if questions. So for the first question, the difference from using a real ammeter would be that the real ammeter has resistance. Because the current is inversely proportional to resistance, the total current decreases. And for the next what if question, If we did this lab using a real battery, the model predicts it would change immediately. However, in real life, this doesn't happen because the resistance isn't actually zero. An example of this could be battery drain or wear and tear. Anyways, thank you so much for listening to my lab, and I hope you have a great day.